Catalytic news. Breaking news. Researchers have found 4 ways to catalyse enzymes. Let me tell you a bit about enzymes. Enzymes are proteins that serve as catalysts. They speed up or slow down reactions but remain unchanged. Each enzyme acts on a specific substrate. The induced fit model describes the interaction between the enzyme and the substrate. The substrate induces a more complete fit of the active site around it. The catalytic cycles begin when the substrate enters the active site. If we were to extract chemicals from a living cell and watch them react with one another, we would probably have to wait a long time to see many reactions take place. On their own, many of the chemicals react too slowly to support the organism's metabolism. Living cells circumvent this problem by producing biological catalysts called enzymes. Enzymes lower the amount of energy required to trigger chemical reactions. By lowering this energy requirement, called activation energy, enzymes make reactions more likely to occur and thereby increase reaction rates. I will now pass you over to Milanka, who is at the scene. Milanka, what do we have there?
It's chaos over here. Scientists have gone mad. This breakthrough is essential though. Let me explain to you a bit about enzymes. Many enzymes use basic catalytic principles. The binding energy is the free energy released in the formation of a large number of weak interactions between the enzyme and the substrate. It can be assumed that the binding energy serves 2 intentions. It establishes the substrate specificity and increases the catalytic efficiency. Here live, we have scientists talking about enzyme catalytic strategies. I'm going to talk about the first catalytic strategy, which is covalent catalysis, and it's when an enzyme's active site consists of a certain reactive group. It's more often a powerful nucleophile which temporarily covalently gets attached to a component of the substrate in the course of catalysis. The example we're using here is chymotrypsin, which contains an extraordinarily reactive serine residue, which is serine 195, which breaks the peptide bond selectively on the carboxyl terminal of the amino acid, such as tryptophan, tyrosine, phenylalanine, and methionine. The enzyme employs a powerful nucleophile to attack the unreactive carbonyl carbon atom of the substrate. Specificity of chymotrypsin is the cleavage of the proteins on the carboxyl terminal of the hydrophobic amino acids. It's shaded in orange in the diagram below, and the likely bonds broken by chymotrypsin are specified in red.
The second catalytic strategy is acid-base catalysis. In general, acid-base catalysis, a molecule apart from water, plays the role of a proton donor or acceptor. The example we're using is chymotrypsin makes use of a histidine residue as a base catalyst to boost the nucleophilic power of serine. In the presence of the substrate, the histidine residue accepts the proton from the serine 195 hydroxyl group. In doing so, the residue acts as a general base catalyst. The withdrawal of the proton from the hydroxyl group generates an alkoxide ion, which is a more powerful nucleophile than is an alcohol. The catalytic triad shown on the left converts serine 195 into a potent nucleophile, as illustrated on the right. Thanks.
The third catalytic strategy is catalysis by approximation. Most reactions comprise of 2 discrete substrates, and each situation the rate of the reaction may be significantly increased by joining the 2 substrates together along a single binding surface on the enzyme. The example we use here is carbonic anhydrase, which binds carbon dioxide and water in adjacent sites to speed up the reaction. Carbon dioxide hydration and the bicarbonate ion dehydration are often coupled to rapid processes, specifically transport processes.
The final strategy is metal ion catalysis. Metal ions function catalytically in various ways. Metal ions have a number of properties that enhance chemical reactivity. Their positive charges, their ability to form strong yet kinetically easily altered bonds, and in some cases their capacity to be stable in more than one oxidation state. A metal ion can enhance the formation of a nucleophile, act as an electrophile, and even serve as a bridge between the enzyme and the substrate. Now I'm going to hand you over to a colleague who will now talk to you about carbonic anhydrase.
Carbonic anhydrase contains a zinc ion vital for its catalytic activity. Zinc is found only in the +2 state in biological systems. The zinc atom is essentially always bound to 4 or more ligands. In carbonic anhydrase, 3 coordination sites are occupied by the imidazole rings of 3 histidine residues, and an additional coordination site is occupied by a water molecule. Because the molecules occupying the coordination sites are neutral, the overall charge on the zinc unit remains +2. At pH 8, the reaction proceeds near its maximal rate. As the pH decreases, the rate of the reaction drops. The midpoint of the transition is near pH 7, suggesting that a group that loses a proton at pH 7 plays an important role in the activity of carbonic anhydrase. The binding of water molecule to the positively charged zinc center reduces the pKa of water molecule from 15.7 to 7. The effect of pH. Once the pKa is lowered, many water molecules become deprotonated at neutral pH, creating a considerable amount of zinc-bound hydroxide ions. Zinc-bound hydroxide ions are potent nucleophiles which have the ability to attack the carbon dioxide much more readily than water molecules. This is Milanka reporting for Catalytic News. Back to you, Misha.
Thanks, Milanka. That's the end of the Catalytic News. Keep catalyzing!